Hi, I'm Nick.
I'm Jake. This is Lab 10, Imaging System Calibration, and we're Wednesday Night Lab.
In our lab today, we are using a lens and camera with a C-mount system in which we have a flange back length of 17.526 millimeters. Otherwise, a CS mount would have been shorter. The flange distance is important because with an incorrect FDL, the image plane will not line up with the sensor. In order to determine pixel size, we set up a microscope objective to focus on the sensor. Using the micrometer on the X stage, we measure the horizontal sensor size. Rotating the camera 90 degrees, we repeat the measure. For the fisheye lens, we repeat the process again. When measuring the field of view, we imaged a ruler across the screen giving us the X distance. With a quick measurement of the Z distance and using some trig, we get the full field of view. Rotating the camera 90 degrees and repeating the measurements will give us the vertical. For the fisheye, we repeated the same process, only it was harder to read. Here are the results of our calculations of the pixel size and full field of view. Our pixel size for the normal lens was fairly accurate with a posted size of being 3.75 micrometers. As expected, the full field of view was much larger for the fisheye lens.
An object in n-dimensional space has n number of coordinates, and you can project that into homogeneous coordinates that will have n+1 coordinates. This is very useful because a real object is obviously in 3 dimensions and therefore has 3 coordinates. However, an image is only in 2 dimensions and therefore has 2 coordinates. Therefore, you can project the image into homogeneous coordinates in order to get 3D coordinates. The Cartesian coordinates can be projected into homogeneous coordinates using the camera projection matrix shown here. This transformation matrix allows you to switch the reference so that you can tell the camera's orientation and position with respect to the object rather than vice versa as before. This intrinsic projection matrix is actually an upper triangular matrix because the bottom left corner are all zeros below the diagonal, and these two matrices combined give you the transfer. This transfer matrix is important because it lets us switch between 2 different pictures. In one of them, the camera is stationary and the object is at different orientations and different positions relative to it. And then in the other one, the object is stationary flat on the ground just as a plane, and it shows the camera at different positions and orientations above the object looking at different angles. Along the y-axis, distortion increases with field height. As you can see here, a square grid with no distortion. And with negative distortion, there's more magnification around the edges, pushing it out, creating the pincushion effect. And with positive distortion, the magnification decreases near the edges, giving this barrel effect, which kind of looks like it's getting pushed out. As you can see from these pictures, distortion has no effect on the center of the image and affects it more as it gets closer to the edge. This is the equation for distortion off-axis. As you can see, the equations are symmetric about y and x. Therefore, the ray error equations are also symmetric because it's just the derivative. And as you can see here, there is a K1 term. What is that? It's the distortion coefficient. We can actually solve for that by going through the equation, and this is what we come up with. Using r equals square root of x squared plus y squared as the normalized field height. And here we get the third order model of distortion.
We started our lab with the normal lens. After measuring the square's size, note we'll need this for calibration, we take the 20 images with the board in varying positions as Jacob is demonstrating. We'll then use these to calibrate the camera. Using MATLAB and CalSci Toolbox, we begin to calibrate the camera. We start by loading all the images and then clicking on extracting grid corners and giving the default answers. We can come back and recompile the corners if need be for errors later. With the first image up, we map out each of the 4 corners as shown here. It'll then ask for the size of the square, which for ours was 38 by 38 millimeters. You may need to answer how many squares are between each corner, as well as any initial distortion coefficients if there are any distortions. If you're good, continue for all 20 of the next images, starting each time in the original corner. With the corners extracted, we can then press calibrate and then analyze the error, correcting any necessary errors if need be. We are trying to get a pixel error of less than 0.1 pixels. After a final calibration, we can then extract our intrinsic values. After calibrating our fisheye lens, we then take a picture of the checkerboard up close. Using the undistort feature, we then process it and undistort the fisheye lens, and as you can see, it looks much better. Once the camera is calibrated, we can then try to determine the angle between the cube that Jacob is holding. By using the first term in the rotation vector that we got from our intrinsic value, we can then calculate theta. Here we've taken a picture with our normal lens of the MTF plot as well as our fisheye lens, and as you can see, the normal lens has a smoother plot of the MTF rather than the fisheye.